We are now going to learn about the torque that acts on a current loop. Now, a current loop, we already know it behaves like a magnetic dipole. And we know the torque acting on a magnetic dipole is M cross B. So we can use the same formula. Let us try and understand that. So here I have a current loop. Okay. Now just let me turn this around a little bit so that you can see that. And the current is flowing in this direction like this. And so you know that this current loop acts like a magnetic dipole, M, which is equal to I times the area of this loop, right? So M is I into A. So if you use this as the magnetic moment of the loop, and then we can just use M cross B. Let me say that right now this current loop is in a region of uniform magnetic field B in that direction, right? So let us say that the angle between B and M is theta. Then we know that the torque is M cross B. M into B into sine of the angle between them, M cross B. So M cross B is going to point in the direction into the board, right? It's going to point into the board. And because it's pointing into the board, what is going to happen? The torque is like this. Pointing into the board means torque is like this. And because the torque is like this, this loop will turn around like that. And when it is like this, M cross B points out of the board. It's pointing this way. Out of the board means the torque is this way, and so it is going to go back. Exactly like what the magnet did, right? It will keep oscillating. So it works exactly like the magnet. And so basically this torque formula is correct. Okay, this formula is correct. We can just go ahead and use it. We don't need to know anything more. We can say that the torque acting on any current loop is M cross B, the same formula as for a magnet. Now at this point we can stop, but if you wait for a minute and think about it, where did this formula come from, M cross B? We derived it by taking magnetic charges, right? And then saying there is a force like this on the north pole, a force like this on the south pole, and that produces the torque, right? That's how we came up with this formula. But magnetic charges, we also know, don't really exist. For magnets, we use this as a convenient way to solve problems, but we know that magnetic charges don't really exist. It is just a nice problem-solving tool. Whereas current loops do exist, right? So using this formula here seems a little bit like cheating, right? It's a bit risky because we are using magnetic charges which don't really exist as the foundation for all the formulas. So that seems like we are taking a lot of risk. What if this itself, the formula was wrong? Definitely we can't use it here, right? So is there a good independent way to derive the formula for torque on a current loop? Yes, there is. And I'm now going to prove this formula. You're going to end up with the same formula. So if you feel like you don't want to worry about the proof and you just want to take this for granted and use it, you can go ahead. But I'm now going to prove the formula, so that way, without using magnetic charges, I can show you that the torque acting on a current loop is indeed M cross B. And for current loops, we know that they exist, and therefore we can use the proper proof for this. In fact, then we can say that a magnet actually behaves like a solenoid or a bunch of current loops together. And so the magnet's formula, right, M cross B, which we have derived using magnetic charges, that formula is also valid because the formula is valid for a current loop. So I'm now going to prove the formula, the same formula that you know for a current loop. We are now going to derive the torque formula for a current loop. I'm going to take this rectangular loop and I'm going to hold it like that. So basically this rectangular loop is what I have drawn there, okay? So this side is L, that side is L, this and this side they are B, the breadth. So area will be L into B because the rectangular loop. The current flows like this, then like this, then like this, and then like that. Now I want you to remember that actually though I have drawn it like this on the board is two-dimensional, you have to imagine that this is three-dimensional. Notice how I'm holding this loop, right? This loop, I'm holding it, the plane of the loop is perpendicular to the plane of the board. This lies on the board, this side lies on the board, this is parallel to the board, whereas these two are perpendicular to the board. So this current is actually coming out of the board towards you. This current here, right, that is going into the board. Whereas these two, this current is going like that and this current is going like this. Anyway, now if I say the current is flowing like this, then you know using the right hand thumb rule that the magnetic moment must basically be pointing like that. Okay, so let us go and do that. So the magnetic moment is of course perpendicular to this loop, right? Perpendicular to the loop surface. The magnetic moment is going to be like that, I into A, so I into area which is L into B, right? So ILB. Now the magnetic field I'm going to say is horizontal like that, so I'm going to draw B like that, and let us move this M there, and the angle between the magnetic moment and B, let us say is theta. Let us say that that is theta. Okay. Now I am interested in what is the force acting on this side, then I'll look at the forces acting on those two sides. So let me first start with the force acting on this side. Now this current is going like that. You know that force acting on a current carrying conductor is IL cross B. L cross B. This is what I should take. B is like this. So L cross B is going to be pointing into the board, right? But what angle should I take? You know that this L is perpendicular to M. So if I draw this there, it will be easier to understand, right? If I draw this here, you see that this L is perpendicular to M. You know that M is basically perpendicular to this loop, you know that. So this is 90 degrees. And so that means IL cross B pointing into the board, well, the angle that I should take is 90 plus theta. Let me show that here like this. So if I hold this loop like this, the current is this way, B is that way. So IL cross B is definitely pointing into the board, right? So I should mark this with a cross. Going into the board. And how much? I into L into B into sine of the angle between them, 90 plus theta. Now what is sine of 90 plus theta? Cos theta. So I can also write this as ILB cos theta, but for now ILB sine of 90 plus theta. Going into the board. What about the force acting on this one? Now well, the current is going this way. So if I mark it here, you can see that the angle between L and B, right? Taking the direction of I properly, L and B, this angle is how much? Well, this is 90, so this must be 90, that is theta, so this must be 90 minus theta, right? And what will be the direction? IL cross B, it is coming out of the board. L cross B is coming out of the board. So here I should be marking it with a dot coming out of the board, okay? So how much will be the force? ILB sine of 90 minus theta coming out of the board. Let me show that again here, okay? So you can see that the current is actually going to flow like this. B is that way. So IL cross B is coming out of the board. Whereas there the current is going that way. So IL cross B, IL cross B, the force is going into the board. Now if you look at these two forces, they are both equal in magnitude. Sine of 90 minus theta is cos theta. Sine of 90 plus theta is also cos theta. So both are the same magnitude, F1 and F1. That's why I used F1. And they are opposite in direction. That is going into the board, this is coming out of the board. Now, but the way I've drawn it, it looks like there might be a torque. That's why I'm using this three-dimensional thing. You can see that this force and this force, they're actually in one line, right? This force is going into the board, this is coming out of the board, they are in one line. I'll show it like this, in one line. There is no torque, right? So these two forces will perfectly cancel out, they are equal and opposite, and they are in a line. You have to imagine that this is three-dimensional, so these two are in one line. So the two F1 forces cancel with no torque. What about the forces on these two? That is easy, right? Now if you look at this one, again let me show you this. Actually the current is coming out of the board and the magnetic field is like this. Coming out of the board, magnetic field 90 degrees, right? Just think about it. This current is coming out like this, magnetic field is like this, 90 degrees. And the force is going to be upward, IL cross B is going to be upward. So if you take this side which is at the top, IL cross B, right? In this case, L is B, IB cross B, right? Small b cross B. So you should basically say B, right? B cross B, B cross B. The force is upward, pointing like that. And how much is it? IBB, I small b, capital B. 90 degrees, sine 90 degrees is 1. So IBB. And if I take this one at the bottom, right? If I take this at the bottom, the current is going into the board. B is that way. So L cross B is going to point downwards. Of course, instead of L, I should be using small b. So it's going to be a force downwards, right? Acting downwards. Here the force is acting up, here the force is acting down, and you can see they are not in a straight line. Okay. So how much will be the force? IVB, but it's going to be pointing down. Now, if I look at these two will definitely produce a torque. Let me show that here. Okay. Now, the force acting on this is up, the force acting on this is down, and they are not in a straight line, right? They are not in one line, and so it's going to basically rotate this loop like that. So let us basically try and find out how much will be the torque. Well, formula for torque is R perpendicular into F. Now these two forces are equal and opposite. So for a couple, I can just simply say force into the distance, perpendicular distance between the line of the forces, right? If I join these two, that will be L. That will be L. Can I say L into F? No, because that is not the perpendicular distance between these two, right? I must draw this line and I must take that perpendicular distance. I must take this distance. I must take this distance. Fully find that distance. I know this is L. Well, for that I need this angle. It will be convenient if I draw this there, right? I draw the same line there, because this is just the vertical line. This is just a vertical line. And you can see that this and this vertical and horizontal 90 degrees, this is theta, so this is how much? 90 minus theta, this is 90 degrees, so this must be theta. So this angle must be theta. But this angle is basically the angle between this and this, right? Because that is L, so you can see that this is also parallel to L. So this angle is also theta. So if I bring that theta here, then that will help me. So this is theta, this is theta. Let me show that here in the three-dimensional case. So here you have these two forces, one force is down, one force is up. This is that line that I've drawn, that green dotted line. And we want the distance between these two, right? Distance between these two. So that's what I want. I've got, this is L, this is L. L cos theta will be this length, which I don't want. I want this, which is L sin theta. So the gap between these two forces, the perpendicular distance between the forces, is L sin theta. So I can use that as R perpendicular. So L sin theta into IBB. So our IBB into L sin theta. Okay? But B into L is area. ILB is M. ILB is M. So MB sin theta, I've got MB sin theta. So I can write the torque is MB sin theta, and you know that it's going to turn it this way, right? You know that here the forces are going to make it turn this way, right? The torque is going to make it turn this way. So I've marked it like that. But you also know that if it is marked this way, it means that vector wise it is actually going into the board. So I can say this is going into the board. Okay, so going into the board, M cross B going into the board, correct, exactly the same thing that we want. So we can write that the vector formula for torque on this rectangular loop, the torque is M cross B. So we have proved that the torque acting on a current loop is M cross B. Okay, so are we done? No, because I only proved this for a rectangular loop. What about a circular loop? What about some other shape? Because you see, we are going to use this formula for all kinds of current loops, not just circular current loops, and definitely not just rectangular current loops. So what do? Well, let me consider some weird shaped loop like this, and let us say that the current is flowing like this. Now this is in the plane. This is in the plane of the board, so I'm going to take it in the plane of the board. Now any loop like this can be cut up into a large number of tiny rectangles. So here is one rectangle, another rectangle, another rectangle, another rectangle. So you can break this up into lots of rectangles. Okay. In fact, you can, if you want all these spaces, you can fill it up. I have left some spaces, but if you want, you can fill all of them up. You will get infinite number of rectangles, but basically you can cut it up into huge number of rectangles. Now if the current is flowing like this, right? So that should be the direction that we want. And so everywhere I'm going to take the current in the same sense, right? Let me show you for this loop. Okay, I'm going to take the current going this way, then going that way. Same current. Okay, now you say, but how do I know that the sum of all these rectangles is equal to this big loop? Okay, so I'm going to show you that. For the next one also, I'm going to take the current like this. So here it's going to go this way, that's going to go that way. Now if I consider both of these together, think of both of these together, at this location, this current and that current, they are opposite, they will cancel. So if I add these two rectangles, you can effectively say that they form one rectangle with current like this. Right? You can ignore the part in the middle and you can say that the boundary is what matters. So when you add up these two rectangles, the currents in the middle, they don't matter, they cancel out. You can see that basically it is I that way and I this way, perfectly cancelling out, overlapping each other. And so effectively you can think of this as one single big loop. What if I take the third one? Again, I'm going to take the current in the same direction, you can see, right? But if you see these two adjoining ones, they will cancel out. So if I add these three up, you can say it is this big current loop, right? And if you keep doing all that for every rectangle, what will you get? You will get this, just the boundary. You notice that when you take adjoining current rectangles like that, when you add them up, effectively you only get the boundary. And if you did this for all the rectangles, what will happen? You will end up with the final boundary, which is just the boundary that we started out with. So yes, all these rectangular loops carrying current added up together is equal to just the current in the boundary. So first you have to convince yourself that what I just said now makes sense. Then the torque acting on this big loop, you can say is the torque acting on this plus torque acting on this plus torque acting on all of these. Now for this one, I can call it I into A1, I will call that M1. Okay, that is the dipole moment or magnetic moment of this loop. For this loop, I will call it M2. For this loop, I will call it M3. And for each of these, I can find the torque. So the torque acting on the whole thing is M1 cross B, because for this I got the formula M cross B, right? So I can apply that M1 cross B plus M2 cross B plus M3 cross B and so on. Everywhere B is the same, uniform B. So it is M1 plus M2 plus M3 cross B. M1 plus M2 plus M3 cross B. Well, M1 plus M2 plus M3 is I into A1 plus I into A2 plus I into A3, etc., which is I into A. I into A is M. So you can write torque is M cross B for this entire loop. So we have now proved that the torque formula that we have derived is not just valid for a rectangular loop, it is valid for any shaped loop, We have now seen that this torque formula is valid for any current loop. But if you take a magnet can be modeled as a solenoid. But what is a solenoid? A solenoid is just a bunch of current loops. So that means any magnet can be modeled as a bunch of current loops. So that means since the current loop has this torque formula, a bunch of current loops will also have the same torque formula. So basically for a magnet also the same torque formula is valid. So for a magnet with dipole moment M, we can say that the torque acting on that magnet is M cross B. And now we have proved this without resorting to magnetic charges. So we have not used magnetic charges to prove that the torque on a magnet is M cross B. Earlier we did that with magnetic charges. Now we have shown that the same formula is valid even if you don't use magnetic charges at all, but just think of the magnet as basically a bunch of current loops.